Алло. Да. Сейчас, 5 секунд.
What the fuck? Он стримит сейчас картинки.
Рыжа как-то? Неправильно же. А, вот эту?
В смысле, он дик? А, подожди, как это сделать? Cancel.
Финансовая страница.
Разработчик сложности. Давай. Стрим.
Ага, да, 3000.
Так. Не надо, сейчас. Попрошу, верните все. В смысле? У меня очень тихий микрофон.
Не, ноут просто нет, девайсы сложно. Да. Ага. Ну, для этого нормально, для такой сети нормально. Сейчас. Смотрите, у Фореля есть такая особенность, то, что его используют для узлов с очень высокой плотностью. Для сенсорных сетей с высокой плотностью. Вот поэтому... А? Алло. Сейчас 5 сек посмотрю. Алло. Слышно? У Фореля, алгоритм Фореля используют именно для сетей с высокой плотностью, именно сенсорных сетей. Да, вот. И тут именно рассчитано для таких. То есть он у вас кластер делает, если там смотреть, блин, я сейчас посмотрю. Алло. А у меня телефон завис. А вам когда нужно сейчас это сделать?
Здравствуйте.
Сейчас упало? А? Сейчас упало? Нет.
Так. Допустим, я его вот так поставлю. Да?
Ты зачем мне звонишь?
Так. Там идет?
Да. Да.
Уважаемые дамы и господа, там бла-бла-бла, вот, посмотрите сюда, там бла-бла-бла. Слышишь, что? А какое подключение у этого микрофона всенаправленного сейчас? Да я думаю, ну ладно, стирать наверное. Можно зайти, кстати, на YouTube, посмотри, как эта хрень снимает. Зайдешь на YouTube, на этот. Не знаешь, этот канал, что ли? Ну, найдешь. Раз, это Харбат. Раз, два, пять. Раз, два, пять. Что произойдет? Раз. Раз, 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 раз. Раз. Раз, раз, раз. Раз. Раз, 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 раз. Раз, 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 раз. Раз, раз. Раз, 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 раз. Раз. Блин, анимацию выключу, я что-то не... Тихо. Очень тихо.
По идее должно правильно быть. Ну как бы. Дистанция между шлюзом и самим нодом, да. Да, хорошо. Я вам напишу. Я вам скорее всего, к 13 часам или к 2, как по Москве напишу и потом созвонимся. Пять 600. Окей, да, понял. Хорошо, тогда пораньше напишу. Да, понял. Дайте.
Подставка вот эта странная. Она, я ее зарядил полностью, она стояла отдельно от камеры, разрядилась вновь.
Там ничего не коротит, ничего нету? Не понимаю. А сколько стоял?
А?
Сколько стояло?
Неделю.
Странно.
Очень. Такого не должно быть.
Она полностью заряжена была, да?
Полностью.
Сейчас если вырубить, все, да?
Сейчас просто сама камера заряжена полностью.
Да. Это я.
Отцепи провод.
Какой?
Да, отсюда.
Почему тут стоит? Греется же.
Ну, не было солнца. Некуда его поставить больше. Ты что, провод вытащить не можешь? Провод вытащить не можешь. Пойду я блогерить. Камон! Ой, ё-моё, надо рубануть трансляцию-то. Надо заново запустить. А то кто-нибудь посмотрит.
А на какой канал, извини, он транслировал?
Ну, типа Роденовский.
А, то есть там 100% куча людей.
Не основной Руденский. Так.
Значит, смотри.
Я знаю, коннектинг у меня к ней пока. Сразу.
Нажми просто на кнопку. Вырубай.
You are transmitting, so
Можно ли
transfer. No, what is more comfortable because if you are you broadcasting this?
Yes, yes,
No,
I'm
no.
Broadcasting очень плохо будет.
То есть у вас нет записи? Вот Белкрова не будет смотреть запись?
Сейчас я пытаюсь сейчас.
А можно подключить будет?
К доске?
Лучше не надо, да?
Не очень хорошо. Не, можно попробовать, но...
It says that it's better to use our...
Okay. Okay. So I will use the black note and not this.
Presentation on USB.
Everything required for the user.
Если будет слышно,
Спасибо. О, смотри.
Тихо ты, вот что-то интересное, очень прикольно.
Да.
По качеству, конечно, сейчас попробую скорректировать.
Очень похож на мой рабочий стол.
Это он и есть.
Не, ну 2R, Google, да. Ой, VirtualBox. Можно на русском читать будете?
На английском.
В смысле на английском?
Итальянский.
А, да? На английском. А серьезно?
все больше шансов.
Почему? Я русский-то не люблю.
Там упало ты уязвим. Елена, а ссылку лучше вам отправить?
Там дыхали интернет-провода.
Да, как вы скажете?
А я не знал. Прикольно. Круто, надо с собой провод носить. А это что такое? Думаешь? А, да, проектор. Да, в Америке в школах на таких. В Америке на таких уроки ведут. Уроки в Америке в школе. Учителя. Да, там у них это типа водного раствора какого-то, они его брызгают на хрень, они просто могут это читать. А то уже давно. Да я еще там еще какое-то было. Это не все страна, да? Я же с Монголии, у нас нет такого.
Вот такой проект?
Ага. Мы об этом еще 5 минут назад закончили.
Интересно, сколько он часов работает? Я думаю, у него лампа такая слабая.
Не знаю.
Ну, очень слабая лампа.
Можно спросить. Вот у парня. Нет, у парня зеленый, можно все ставить. Он будет на итальянском или на английском? Какая на итальянском будет рассказывать?
На самом деле на английском.
Что он сказал?
Что он обещать не буду. Ну, я запутан.
Сидим тихо. Чтобы отсюда. Или вообще.
Пересесть?
Да нет, нет, ну или пересядьте вот туда, да. Чтобы меньше шумов на это было.
Окей.
Он просто очень близко ловит.
Со звуком.
Я чувствительность подкорректирую, не переживай. Пока нормально.
Я выбираю делать неправильно. Тем более, кто мотив болел. Боялся уже заскал тебе долго.
Сейчас все затихнут.
Сядь корни. Сядь корни. Ну да, его попроси, он нормально. Он неплохо. Ну все. Не знаю, я вот ну как бы, первый защитник, у меня был
У нас начинается лекция. Пожалуйста, потише. Давайте послушаем. К нам приехал из Политехнического университета Милана, это Италия, профессор Марко Грибауда. Может быть, некоторые уже были, точнее, может быть, некоторые были в прошлом году на школе, на молодежной, которая у нас проходила. Это был октябрь. И там профессор Марко Грибауда читал лекции, такие вводные, да, в теорию массового обслуживания. И там были даны основные понятия, которые связаны с случайными процессами, с марковскими моделями. Здесь более такой усложненный курс, но поскольку практически большинство это студенты 4-го, до 5-го, 6-го курсов, ну есть некоторые студенты 3-го курса, и практически все слушали курс теории массового обслуживания, поэтому данный курс вам должен быть понятен. Но хотя бы тот бэкграунд, да, который у вас есть, он будет достаточно для того, чтобы вы поняли материал. Professor Marco Grimaudo, could you please introduce your university and lead department?
Okay, so
As well as maybe say words about your research studies and how these research studies are related to the topic of our lecture.
Okay, very complex question. So, nice to meet you. Some of you have already met me in October. I already remember some faces. And okay, I am Marco Ribaldo, I am at Politecnico of Milano. Milano, as you know, is one of the main cities in Italy, probably the second biggest city after Rome, which is in the northern part of Milano. Probably some of you know is the fashion capital of Italy, because it is the main fashion city. And in Politecnico of Milano, they also have some course about fashion. And actually, I also teach something in the course of fashion, but for different reasons. So, Politecnico of Milano is a very big institution. It has different poles where courses are given, so not just the city of Milano, but also the city of Lecco, Mantova, Cremona, Como, which are many important cities in nearby Milano. And it has many curriculum, but mainly in engineering. So they teach civil engineering, electrical engineering, computer engineering, plus architecture, and they have also a course in design. I am in a department which is called DABE, Department of Electronics, Informatics and Bioengineering, which involves all this type of activity. Actually, it is a huge department. There are around 600 people in the department, from PhD student to full professor and administration staff. So it's quite a very big department. As my activity there, I mainly teach several courses in two main areas. One is my research area, that is performance evaluation, and it is the topics to which this seminar that I'm going to start today belongs. Then I also have some passion just because I like the subject, which is computer graphics, so I also teach computer graphics and some derivative of computer graphics. For example, in the fashion course of Politecnico di Milano, I teach a special software that is called Modaris, which is what you do to draw the piece of garment that you have then to cut to produce dresses in a big scale. It's very strange, completely unrelated, but since I like computer graphics, there was this opportunity of also teaching that type of course, and I took that opportunity. For what concerns performance evaluation, I have two courses in performance evaluation because, as I told you, the Politecnico of Milano has several institutions, so I'm teaching it both in Milan and Como, but unfortunately they are engineers, so they want something very practical. So even if my research is something that is more, let's say, mathematical, I can only teach in the performance evaluation courses the very basics of queuing network and simulation and analysis of system with queuing network. And I'm also interested in dependability, so I also teach part of the course on dependability, and there I can do Markovian model, continuous time Markov chain, and similar subjects. As my research, I started with my PhD on fluid models for performance evaluation, where actually we were trying to use Markov chains characterized not just by a discrete state space, but also by a continuous state space. And so all the theory and all the modeling approach that are called fluid models are the one in which you try to use some continuous quantity together with the classical discrete one, and you combine them together to handle different larger system. After studying that, let's say that this the continuous aspect that was in this type of fluid model led us to approach mean field analysis, which is the topic that we will be presenting today. And from mean field analysis, we exploited it to describe system composed by a large number of identical objects that interact together. And with that, me together with Professor Andrea Bobbio and Davide Cerotti during his PhD, created a formalism that we call the Markovian agents, which in a few years became quite popular, maybe by the work from some English guy, Jane Easton, Jeremy Bradley and William Knoppenberg, who applied it more from process algebra to describe agent-based systems. So we were, let's say, the first inventing this type of approach, which was later expanded and much more studied by other researchers, and now it has become very popular and one of the few ways in which you can study a system that is very big and very complex, provided that that system is composed by very similar things that operate all in the same way. Okay, and this will be the introduction of these topics of this seminar of this week. I am from an engineer faculty, so it's very important to tailor this type of analysis to application. And so in the last year, I have applied most of this knowledge to communication networks, so to study communication protocol, but also to study cloud computing, so allocation of virtual machine in cloud environment, or study big data application, big data framework, etc., etc. So now the main application of this area came from big data, large computing infrastructure, because those are the things that are studied in this main in Polytechnic. Okay, I'm not sure if I have said everything. What I'm missing? Okay, so this was an introduction about myself and my research work. So, okay, let's start with this mean field analysis. This is so cool. So, first of all, as I told you, some of the reasons for which this topic is important today. Mainly, I came from engineering, so data center, which is where computation is currently done, are very complex buildings where there is a lot of IT devices. We have servers, we have a lot of network equipment that interconnect everything together. We have storage units, so a lot of disks, because we have to put there a large quantity of data, and we want to study this type of system. Okay. How is computation done nowadays? Up to a few years ago, we had one server, a big PC, where you install your operative system and your application, which was, it's very nice, but it have very poor resource utilization. So nowadays, the big data infrastructure no longer have one server with one operative system and one application running on the operative system, but we have virtualized resources. So everything is virtualized. Every application operative system thinks to be on some hardware that isn't there, and there is some software level that translates what the application thinks to have below to what is actually below and what is actually running there. So everything is virtualized. And by virtualizing, not having a real server, but let's say using this software structure that makes application think that they are running on a real computer while they are just running in some confined environment, how to consolidate servers. So on one single machine, put several virtual machines, so that the hardware that once upon a time was used to run just one server now can run several of them in parallel without them fighting with each other and crashing one into another. And this is also done using cloud provider, so that you no longer buy one server, but you rent from some cloud provider the ability to run your virtual server and install everything on this virtual server. And these are the system that is today. Computing science, computing infrastructure that execute things today are done in this way. And studying this is very, very complex. What runs on this infrastructure? Well, we all now are in the era of big data. So users no longer are just happy to have a large PC that store the name of their customer and all the order that they were able to deal with, all the goods they have sold, etc., etc. They want to have large analytics, something that study the users and depending on what they have bought, suggest them to buy something else. And this is all the topics of big data analytics, something that by matching all the goods that a user have bought and comparing with what all the other users in the system have bought, decide what to suggest them to buy next. Okay? Also, we want to run very large scientific experiments and simulation. We now are in the era of space, radio telescope, very big data, also DNA sequencing to produce tailored medicine for very specific pathology. And for doing this, we have to match a lot of data about pathology of other people, etc. And also, we want to have high quality multimedia elaboration. I do not know here in Russia, but I think even here, many of you use Google, and sometimes Google presents us some very rich movie made by the photo that they found from 1 year before and creates this very complex animation just to make people love Google. But also we know that we can upload our video, they are converted, we can elaborate them, add whatever, and all this requires a lot of computation, which is done by this very big data center infrastructure and using virtualization. There are a lot of technologies. These are probably most popular in the engineering field of view, but you might have heard of OpenStack, which is one of the main things that allow cloud computing to exist. You might have heard something like Chef, which is how you can store terabyte and terabyte of data in a very large distributed fashion. You might have heard about 3 layers networking to create the connectivity inside the data center to allow all machines to talk with each other without having bottleneck in the internal infrastructure. And you might also have heard about NoSQL databases to perform big data and analytics and have treat very big amount of data. Okay, so this is the type of problem that computer scientists now want to have to deal with. And of course, well, MapReduce is another paradigm used to handle very big data sets by dividing them into smaller pieces that can be run in parallel and all the results collected to have the result. It's very complex. So, of course, I'm not saying anything about these technologies. There are courses and courses at the university specifics for each of these points because they are where things, they are very important and they are how things are currently done to, let's say, do the extra type of application that nowadays we can do and up to 10 years ago we weren't able to do. The problem is that users would like to run this application in time. So we want to provide service level agreement and give users acceptable behavior. There is no need of something that can suggest a customer what to buy next in 1 year from now. If now I have bought the new Star Wars movie, it's not likely that something will suggest me to buy Star Trek movie 2 years from now. Okay, it must give me something very, very quick. So, in order to have some service level agreement and be able to do all these things fast, there are 2 approaches. One that is the classical done by people in software engineering is monitor the performances and automatically scale the system. I see things are running slow, then I will add another server and see it is fast enough. It's not fast enough, I will add another server until I reach the desired goal. Which is okay, and in some cases it works really, really well, but there is another way. That is, try to predict the performances of the system and use such prediction to correctly size the infrastructure. Okay, this is where I work, and probably also what would be more in line with your area of expertise. Try to use some sort of mathematical models so that we can predict how much time will some of the previous application take to complete, so how much will my MapReduce activity require to compute a NoSQL data query that is working in a network that has a tree-like infrastructure and uses Chef to store all its file system and OpenStack to provide the virtual machine. This is the type of questions that we might like to want, and we might want to address these questions using models. Okay. I assume that all of you here have some experience in how to create mathematical model of things and how use some mathematical tools to analyze them. The problem is this type of application that we want to study are generally too complex for the classical technique. You cannot analyze this very big system with a simple Markov chain because the number of states will simply be too much, or with a queuing network. They are too complex, there are too many interacting entities, and the final outcome, the final performance will depend on how things communicate one with each other, how things talk together. And this will make things very, very complex to handle, and also they are not easy to measure and study. Whenever you have thousands of things going on in parallel, understand which is the slowest, which is the fastest, where is the bottleneck, is something that isn't that easy to measure. Okay? So these are all problems that we have to face somehow. If we try to do the conventional techniques, such as queuing network, the state space is able to explode very soon, and we might not be able to handle and provide accurate measurement in a reasonable time of system of the complexity that I have introduced. Okay, so what can we do? Of course, we cannot create a simple Markov chain, but we have several different tools to find some solution, even if the problems are very hard. One could be using some sort of bounding or asymptotic analysis. So, starting from the system, try if we can find some simple equation that might describe them, and find some reasonable bound to the performance. Very interesting topic, but it is not the topic of this seminar. Fluid modeling, which was, as I introduced you, the point from which I started, could be another opportunity. Fluid modeling means having not just discrete states, but also continuous states. So when we have thing that is very, very large, instead of considering 1 million of objects, I just consider a continuous number which values is 1 million. And maybe handling continuous number is much easier than handling discrete number when they can become arbitrarily big. Another interesting topics, but is not what I will be presenting you today. What I will be focusing on is on mean field approximation, which will be the topic of today, and also on Markovian agents, which will be what we will be dealing on Thursday and Friday. Okay? So, I hope that I wasn't too boring, but just to give you an idea why we might need this type of techniques. Of course, there is some price we have to pay. The techniques that you see here are all approximation. They will be an approximation of the result that the model might compute. And again, as you know, a model is always an abstraction of the system. So this is making things, let's say, worse from a quality point of view, because we are approximating a simplification, a model of a real system. But in many cases, even this approximate solution to an abstraction of a system can provide some meaningful insight that might help us in actually supporting this type of application. Okay? So, what I'm, let's say, selling you today is better because it can handle very large systems, but worse because it will provide simplified approximation of something that is already an abstraction. So we might have something that is very different from the reality. Of course, we cannot have anything for free, and there is always some type of price to pay. Okay? Okay. So let me start with the real topic of today, that are mean field model, and let me start with what I assume you know. Okay, so let me start to do some refresh on continuous time Markov chain and their use on platform. I am assuming that you know this type of subject. Please, Irina, tell me if they will not know, and I will try to cover the gap as quickly as possible. But they should.
Continuous time Markov chain имеется в виду случайный процесс.
Okay, they know it.
Yes, yes.
Yes, of course. So, a continuous time Markov chain is a special type of stochastic process when we have a discrete state and a continuous time. So, we are considering a process in which we have a finite set of states, and the system will remain for a given amount of time, actually an exponentially distributed amount of time in each state, and then it will jump to another state. Okay? Also, you should remember that they are characterized by a matrix that is called the infinitesimal generator, and this infinitesimal generator is such that, okay, for each row, one element of the row of the matrix will tell us, for every element that is not on the diagonal, the rate of a Poisson process which describes the frequency in which the system will jump from the current state I to another state j. And the diagonal is used to simplify a vector representation of the equation by including the negative of the sum of all the other elements on the row. Okay? With this notation, we can have the so-called transient analysis that will tell us, starting from an initial probability distribution of the state in which a system can be, will allow us to find the probability that the system will be in a given state at a given point in time. Okay, so we have this simple differential equation. If we study this differential equation, we will know for every time t which is the probability that the system will be in a given state starting from an initial point. And if there are some conditions for which the system can be said to be ergodic, we can find a steady state solution, which is where this probability will go as the time goes to infinity, by simply solving a very simple linear system of equations. Okay for everybody? Ready? Okay. A simplification of Markov chain that is used in performance evaluation is the birth-death process. In the birth-death process, we have some counts, and birth-death processes are usually used whenever we want to model the count of the member of a population, and each state accounts for the population of the system at a given time instant. Okay? So, for every time instant, we might have something that will increase the count of the population, that we call birth, and let's say it occurs at a given speed, lambda I, which might be different for every state of the chain, and we might have a probability that the population will decrease at another given rate, which is called, which here we will call it mu. Both the birth rate and the death rate are measured in event per time units. So, for example, in seconds at -1, how many births I have per second, how many deaths I have per second, and both will describe something, some counting that will increase. Okay? Rate might be dependent on the states, and this is the way in which we use it, for example, to model specific types of queuing. Okay? So, all rates can be dependent on the state, and if we have the two, we have the possibility of a birth of a rate, the two events will be concurrent, and the system will move to the next state according to which one of the two occurs. Okay, so when we have a birth process, we are usually interested in knowing the so-called state probabilities. So the probability that the system will be in any of these states in a given point of time or as the time goes to infinity. Okay? The number of states can be infinite, however, if the system is stable, so we have that the speed at which the system returns to zero is faster than the speed at which the system goes to the infinity, the probability of being in higher and higher state will tend to zero, so even if the system is infinite, the probability of having a larger number will be zero. Okay, let us start focus on the MM1 system, okay, where I have an arrival rate lambda and a service rate mu, okay. This is the classical queuing system. So, do you remember how you analyzed it with Markov chain? Okay, it's very simple, so I use to go. Okay. Might use them. Okay, but probably if I use this, people will not see it. Let me check if I can use something useful. No, there is that because people see, I'm not sure whether they will be seeing what I'm writing. So I was. They're working, but would they be able to see?
See? Yes, I think yes. Ну вот видно. Да?
Okay, so okay, so classical MM1Q. Okay, we have the arrival at rate lambda, service at rate mu. Start, we have one state where the system is empty, then we have an arrival, we will have a job, we will have two arrival, we will go to a state of 2, etc., up to the infinite, and in each state we will return to 0 at a given rate. Okay? Okay, very simple. This is okay for everybody, nothing new for everybody? No. Okay. Birth in this case corresponds to arrival at rate lambda. Services correspond to that at rate mu, and this will give us the evolution of the process. Okay. If you remember, there is another type of system that is called the MN1K with a maximum capacity of K. It means that the Q have a finite capacity 1, 2, 3, 4 up to K, and when we reach the final capacity K, something will happen. Depending on the type of system, we might have some blocking, so the arrival process will stop, or we might have some losses. Arrival will continue to arrive, but if they arrive with the system full, they will simply be lost. Okay? Doesn't matter which one of the two we have, the Markov chain that describes the system will be always the same. In this case, we will have K plus 1 states. So we will go up to the final state K. So arrival, we will have arrival up to one final state K, and then we will have service from state K back. Okay? So this is the typical MM1K system. Okay? Okay for everybody? Yes. Now, questions for you. Let us focus on this other system in which we do not have one Q, but we have two identical Qs. So, we no longer have just one, we have two. Okay? And to simplify our description, let us imagine that we have a simple M, 1, 2 Qs. Okay. So, no, I cannot use this. This is too difficult for me. I mean, one who is not as bad as me might use Unity, but unfortunately I was using electronic board for too much time now, and I have lost the ability to use manual writing. Okay, so we want to have that system with two MM1, 2Q. How will we make it? Okay, let me say something more. These are two MM1Q. Okay? What does it mean? We might have that jobs will arrive 1, 2, 1 and 2 here. There might be some cases in which we have, let me write it here. We already have one queue that is full because it has one job here and the other. And the next one randomly chooses to go again to that queue. Okay? So, what we imagine is that we have this system with two MM1, 2Q, and if some job has bad luck that even if the second queue is empty, chooses the one that is full, it will be lost. Okay? So jobs aren't intelligent, they cannot see what's in the queue, they will try to go there, they will toss a coin. If the coin is head, they will go here. If the coin is the other, they will go down. What if the coin tells them to go to the queue that is full, they will be lost, even if the other is empty. Okay? So this is the idea of the process. How can we write a Markov chain for this system?
So you use two numbers for analyzing this statistics?
Maybe we can use two numbers. Yes, so we can use a state with two numbers. So for example, we start with a system that is empty, what this Q number will represent? We have 2 Q. If we have 1 Q, one number represents
The number of jobs in each.
exactly. Each of these numbers will represent the number of the length of the queue. So initially they are both 0, meaning that both stations are empty. Okay? Okay. So, what can happen when the system is empty? Can some service occur? No, because there is no job in service. So this mu here doesn't count. We can only have arrival. Okay? So at the rate lambda we will have an arrival. A job will arrive, lambda is 10 per second, so every second 10 jobs will arrive here. They will toss a coin, and 1/2 of the time they will go up, 1/2 of the time they will go down. So how can we model this thing? So let us imagine that this here, let me call number A, represent this Q. And this number here, B, represent the length of that Q. Okay? So, what will happen now? We cannot have service, we can just have arrival. Arrival arrives at a rate of lambda, 10 per second. Okay? So, if this 10 per second, 1/2 of 10, which means 5 per second, will go to QA. And 5 per second will go to QB. Okay? How do I represent it here? So let me focus on QA. Okay? I will say that here, if lambda was 10 at 5 per second, lambda divided by 2, I will go to one state here. But if at this rate, lambda divided 2, the coin toss will tend to go to station B, I will go to another state. So this will mean move across A, and this will mean move to B. Okay? Okay. So now help me. What number will I have to write there? 0, 1 or 1, 0? 1, 0, because we've said that the first represents the first Q and the second Q. Okay? And here, since we move around B, we will go to 0, 1. Okay? Okay. Now, let us focus, for example, on the case over here. We have here, we have 1 in A and 0 in B. What can happen now? Service. We might have the service. How many services can happen? 1 or 2? 1. Because only QA has one service. Okay? So we might have one service. If we have the service of QA, which will be the next state? 0, 0. So we might have a return here at rate 0. Okay? Can we have also some other events occurring in this state here? Yes. How many? 1 or 2? How many volts for 1? How many volts for 2? Somebody hasn't voted, so let me repeat the question. We might have some different events. How many events can we have here? How many votes for 1? How many votes for 2? How many hasn't voted? Okay. Actually, the right answer is 2. which are the two events that can happen? Again, the job will arrive. Toss the coin. If it says A, it will go to A. So we might have and move A, or we might have a move B. Okay? So, which will be the state after move A? 1, 1. No? 2, 1, 2, 0. Which will be the state after move B? 1, 1. At which rate will occur move A? Lambda half. Because at 10 per second, half was as 2A, and here it will be lambda 2. Okay? So, now we have finished state this and state this. Let us move to this state. What can happen now? How many events, how many arrows will leave this state? 1, 2, or 3? How many votes for 1? How many votes for 2? How many votes for 3? How many doesn't vote? Okay, current answer is 3. Which are the 3? We have service, because now we have one job in B. Okay, so here we will have a service, new. We might have arrival of A and arrival of B. If we have the arrival of B, to which state we will move? A new state called 0, 2. Because if B arrives, we will have 2 of B. We might have an arrival of 1, and if we have an arrival of class A, we will move to 1, 1, which is already there. Okay? So, we will do together just this last state, and then I will complete the chain. Okay? From here, where can I go? How many events can happen here? 1, 2, 3, 4, or 5? How many vote for 1? 4. How many vote for 4? Yes, the answer is 4. So, now let's start with the simple one. The simple is the new arrival. Okay? Let me say that another of A will arrive at speed lambda half. The new state will be 2, 1. Okay. Then let us imagine that we have an arrival of B at speed lambda half. The next event will be 1, 2. Perfect. Okay. Now, the other events are services. So, the service, now we have 2 jobs, so we can have the service of job A or the service of job B. So, we will have 2 arrows. If the service is of job A, it will go in job B, it will go in that direction. If it is job A, it will go in that direction. But now the question is, at which rate this event will occur? 3 options. Mu. Mu half, 2 times mu.
2 mu. The highest mu.
The total rate out of the system will be 2 mu. But each of these will occur at rate mu. Because those servers are independent and each one works at rate mu. Okay? I still want you to do, let's say, this state. We are here. How many events can we have? 4, 3, or 2? 4. No, the answer is 3. Which one we cannot have? This is an MM2 queue. So, it allows a maximum of MM1 to queue. Allows a maximum of 2 jobs per server. So, if one server has already 2 jobs, it is full. So, which is the arrival with the event that we are missing? The arrival of a job to station A. Because if a job arrives, toss the coin, and it gives A, it will be lost. So, we cannot have an arrival of A. We might have an arrival of B, and if we have an arrival of B, we will go down there. Okay. We might have a service of A, and go here. Sorry, we were focusing on this state. So, if we have an arrival of B, we might go this state to 2. We cannot have an arrival of A, but again, we might have a service of A and a service of B. Okay? And now we can complete the game more or less in the same way, everywhere.
По поводу системы MM1.2 мы обычно на 4-м месте отмечаем длину очереди, да? Но в англоязычной литературе обычно пишется общая емкость системы. То есть имеется в виду 2 – это общая емкость, одно место в очереди, один прибор.
Probably it's better that they have not understood what she said. Okay, so the only difference is the last state in which both queues are full, so any arrival will be lost and we can only have services. Okay for everybody? Okay, so this is the solution, which should hopefully be exactly what we have. Okay? Okay. Now, if you like this game, we are going to repeat it. If you do not like this game, we are going to repeat it anyway, so I hope you liked it, otherwise it will be annoying the next part. Okay. I have cleared the blackboard because if you still want, you have it here. Okay? Now, which will be the new game? We will still consider the same type of system. Okay? So, again, a system where we have two queues identical with capacity equal to 2, exactly as before. But now, the arrival in Binjob will be slightly more intelligent than before, and will do what everybody of us will do at the supermarket. If they arrive and there is one queue empty and another full, will join the empty queue. Okay? So they will apply the so-called join the shortest queue policy. Jobs still arrive at rate lambda as before. They are both served at rate mu but by both servers. So this is rate mu, this is rate mu. Okay? But they will always join the shortest queue. Okay? So, very similar to before, but now jobs join the shortest queue. So, again, we will use a Markov chain. Again, this will have two components, one representing queue A and the other representing queue B. Okay? What happens in the join the shortest queue policy if the two queues have equal length? So we have both empty or both with one single job. Okay? In the join the shortest queue, they are identical. There's no reason for choosing one or another. I toss the coin and randomly join any or before. So if both queues have the same size, either they are both empty or they have both the same number of jobs, we will randomly choose any of the two. But if one of the two is shorter than the other, the new arriving customer will join that queue. Okay? So, let us start to play this game again. From here, how many events can occur? One or two? Two. At rate, lambda, lambda half, 2 times lambda, lambda half. Okay? Two events at lambda half because they are identical, so this is exactly as before, because in this configuration, the system works as before. At rate lambda half, there will be a job directed to QA, so the system will go to 1, 0. And at rate lambda half, the job will go to this other state, 0, 1. Okay, this is done. Here, how many events can occur? 2, 3, or 1? 1, 2, 3? 2 events. Which are the 2 events that can occur? Service is the easiest one, so this job will be served. The system will return here at new. And then the arrival. The arrival, since it is joined the shortest queue, will lead the system for sure to state 1, because the next job will for sure join the empty queue. And at which speed will this event occur? Lambda half, lambda, lambda, lambda. Okay. So for sure here we will have an arrival at rate. Questions? Can we go from state 1, 0 to state 2, 0? No. Okay? Because from state to 0, we cannot go back. We cannot return. Okay? Okay. So, this is done. And of course, in a similar way, we will be here when we have 0, 1. All the arrival at rate lambda will bring the system to state 1, 1. But if we have the service will return the state new, and there will be no way of reaching state 0, 2. Okay? So that will be separated. Okay for everybody? This is also done. So we need to do this state 1, 1. How many events can occur in 1, 1? 4? 3? 2? 4. They arrive. 4. We have the 2 services. The job in QA may finish and speed new. The job in QB may finish and speed new. We might have an arrival. Since now the 2 queues will be equivalent, the new arrival will toss a coin. Half of the time will join A, half of the time will join B. Okay? If it joins A, it will go to a new state that will be to 1. If it joins B, it will move to another state which will be 1, 2. Okay? Let us now focus on this one. How many transitions can we have? 3? 3. You are right. Which are the 3 transitions? We will have
2 services.
2 types of services. So, one service will be the service of A, that at right new will bring me the system to 1, 1. But there's also the possibility of a service of class B. And if we have the service of class B, we will go to that state that wasn't reachable before. Because if the job that finishes is the job of type B, we will move to a system, a state in which we have one queue with 2 jobs and the other with 0. Okay? And if there is one arrival, since it is joined the shortest queue, the arrival will bring the system to state 2, 2. But now, at which speed this arrival will occur? Lambda. Okay? any jobs that arrives here will go to the next station. And of course, similarly also for the symmetry state. So at right mu, we will go here, at right mu, we will go there, and at full rate lambda, we will go here. Okay? Okay. We've done this, we've done this. So from state to 2, everything is simple. We must have mu and mu, only the two services occur. Every job that arrives will be lost. Okay? From to 0, what we can have? So, how many transitions? 1 or 2? 1, 2, 3, no, 3 now. 1 or 2? 1, which is the one that you can have? We can have one surface because we have 2 at rate mu. So at rate mu we might go there. Are we done? We have an arrival because the other is empty, and if we have an arrival it will for sure join QB. So at the full rate lambda the jobs will go there. And of course we can have the symmetric here. So total rate mu will go here, and rate lambda will move the system. Okay? So, again, we have a Markov chain. If we compare it with the one before, the difference that we spot are here. We do not have this lambda half, because now when there is an asymmetry, the system will be forced to move to the state that is balanced. Okay, so this is not here, this is not there, and here we will not have the arrival. The arrival here will be at full speed because everything will move to the next section. Services instead will be identical, and the system will move at rate mu in whatever direction. Okay? Okay. So, okay. Now, this was a simple model, very simple, because it was considered to have two stations with k jobs each. Okay? What would happen if instead of 2q we would have 4 of them? Should we have 4, both for the JLSQ case or for the original case? The state will be characterized by 4 components. And each component will be able to go up to 2 in that component. So there will be a total of 3 possible values for each component. We have 4 components, so with 4q of capacity 2, we will have 3 at the power of 4 different states. In general, if we have nq of capacity k each, we will have a total of k plus 1. The plus 1 is the empty system, the 0, at the power of how many q we have. Okay? And this will be always in both in the join the shortest q and in the random capacity. This will not change because, as we have seen, even in the join the shortest q, we might have all the possible intermediate state due to services that can occur in the middle. So for them, all the possible states could be used. This might be quite annoying. There is, however, a solution that we can apply, exploiting the fact that these stations are all identical. So they all behave in the same way. Okay? If we would have, let's say, the second queue that is smarter, and instead of going at speed mu, it goes at speed 3 mu because it's much faster, then we could not do anything. Okay? But if all the things are similar, there's something that we can do to reduce the complexity of the model and reduce the size of the state space. Okay? Are there cases in real life where things are all identical? Lucky for us, yes. In some cases, we want things to be completely identical. Just think about communication protocol. Mobile phone can work because every mobile phone, regardless of the brand, works in the same way for what concerns connecting to the provider and give us the line. Networking, there are many cases in which things, in order to work, are based on the fact that all the things must behave in an identical way. Okay? So, saying, okay, here the two things are identical. If they are identical, we can exploit something to have some better result. It's nice, and we can actually use it. Okay? So, before moving on to this next, any questions? No? Okay? Okay. So, what can we do? Well, what can we do is written here. So, here we have one state in which we represented how many jobs any queue has. Okay, so here we will say this is queue A, this is queue B, this is queue C, this is queue D. And for each of the queue, the component of the states tell me how many jobs it can have. Okay? The alternative could be first consider how many different states a queue can have. Here, since the capacity is k, each queue can only be empty and one of two possible jobs or have two of a possible job. Okay? So, one alternative is to represent a queuing system like this. Instead of one component per queue, which tells me how many jobs the queue has, is counting how many queue have a given number of jobs. Okay? So, instead of representing, let us return to the easier first case that we used. Okay? Instead of having just a tuple that tells me how many jobs have each of the queue, I will use a triplet, 3 values. In the first value, I count how many queue have 0 job inside. In the second, I will count how many queue have 1 job inside. And in the third, I will count how many queues have 2 jobs inside. Okay? They cannot be more because we are in MM1, 2 queue, so each one can have at most 2 jobs. Then they will be full. Okay? But here we are using 3 components. First, we were using 2. Are we sure that this will reduce the number of states? So, before we had 9 states in all cases. If we use this, will we have less states? I am telling you soon. So let us verify that it really happened. Okay? Now the question is, which will be the initial state? Will it be state 0, 0, 0? Yes or no? No. Because now this counts how many Q have that many jobs inside. So, since we have 2Q, the initial state will be one in which we have 2 empty Q, which will not be state 0, 0, 0, but it will be state 2, 0, 0. Okay? Because we have switched. Instead of counting how many jobs have each Q, we are counting how many Q have the given number of jobs. So, in this case, we have that 2 Q have 0 job, 0 Qs have 1 job, and 0 Q have 2 jobs. Okay? This is the state. And we can do this because all the Q are identical. So, knowing if me and you are identical, knowing that I have 1 job and you 0, or you 0 and I have 1, will always be 1 Q with 1 job and another empty. Okay? Okay. So, in this case, when both systems are empty, we might only have an arrival. Okay. If there is one arrival, and the arrival is routed to QA, which will be the next state? 1, 1, 0. Because we will have 1 Q with 1 empty, 1 Q with 1 job, and another empty Q. If the job is routed to the second station, which will be the next state? 1, 1, 0. Because even if it is routed to the second one, we will have 1 empty Q and 1 Q with 1 job. Because now the two are identical and there is no reason, no difference in moving to one or to the other. Okay? So, at which rate will this event occur? Lambda. Because now, regardless of what the coin will toss, it will go to a state in which we have one empty and the other full. At rate lambda half, the one empty will be QA. At rate lambda half, the one empty will be QB. In any case, in both cases, we will have one empty and one full. So when we group everything together, at rate lambda, full lambda, we will go to the state 1, 1, 0. Okay for everybody? Okay. This is done. State 1, 1, 0. How many events? 1, 2, 3, 4, 2. 2 events. So, one event could be the arrival. Okay? Well, actually, no, 3 events. The answer would have been 3. Because let us imagine that we have one arrival. Here, we are in a case in which the Q has one that has 1 job and the other that is empty. The next job will arrive and toss a coin. If the coin says A, it will go here. But if the coin says B, it will go there. Okay? So, in this state, we might have 2 arrivals. Okay? So, if we had 1 empty and 1 full, the new job might be directed to the empty or to the full one. Okay? So, if it goes to the empty, the system will move to state 0 to 0. Okay? So, if it is directed to the empty, it will go instead 0 to 0. But this will occur only half of the time. Okay? If instead it will be routed to the other, it will go to state
0, 1, 2, 0,
no, we will go to 0, 1, 1. You're right. Because we will arrive to, no, sorry,
wait, 1,
1, 0, 1.
yes.
Because if it is routed to the queue that already have one job, we will have one empty queue. The one that previously was empty will remain empty, and the other one will go to the we will have now one queue with 2 jobs. Okay, so let us repeat this. The situation over here is when it goes to the empty. So we were in that situation like this: one job up and the new job goes here. So we will have 0 empty and 2 with one job, and this one still at lambda half will be the case in which we have one full and the new one goes to the full. So we will have one queue with 2 and one queue that is empty. Okay? Okay. Now the service. So we might have one service. Okay? The service goes at rate mu, and it will go from this direction to that one. Okay? Okay. This is done. Okay. So let us now focus on this. Here we have one full queue and one empty one. Again, we might have some arrival and we might have some service. Okay. If we have the arrival, where the arrival will lead us? The arrival can only be at the empty one, because the other is full. And if the job chooses to go to the full one, it will be lost. Because the hypothesis that we have is that if we choose a path that is already full, the job will be lost. So, system will change state only if the job chooses the empty queue. Okay? So, here we can only choose the empty one, and to which state it will move? 0, 1, 1. Okay, so at speed number 2, we can only go to 0, 1, 1. Okay. And we might have one service from the state that have 2 jobs. In that case, the queue that had 2 jobs will finish one service and will remain with 1. So, where we will move with one service to state 1, 1, 6. Are you following me? Please ask me if something is not clear. Okay? Okay. This one. We have 2 queue with 1 job. What happens for the arrivals? They both have 1 queue, 1 job in the queue. So, we are in a case in which the 2 are equivalent with 1 job. If 1 job arrives, it can either join the first or the second queue. In both cases, in the end, we will have 0 empty, 1 with 1, the one that wasn't chosen, and 1 with 2, the one which was chosen. Okay? So, at rate lambda, the full arrival rate, the system will move to state 0, 1, 1. Okay? What if we have one service? If we have one service, we will go from state 0 to 0 to state 1, 1, 0, because one of the queue which had one job now was made one service, so it was returned empty. In the end, we will have one empty and one full. Okay? I made a mistake. Which mistake I made?
We have 2 meals.
We have 2 meals. Okay? Because we have 2 services that are going on in parallel. We do not know which one will end first. They are 2 exponential distribution. The minimum of 2 exponential distribution is still exponentially distributed with the sum of the rest. So here must be 2 times. Okay? Okay. This is done. Now this table here. Here we might have one arrival only if it chooses the one with one job. Because if it chooses the one with 2 jobs, it will be lost. Okay? So from here we go just at rate lambda alpha, because it's the only one that can occur, to one state in which we will have 0, 0, 2. Okay? Since only if it chooses the empty one, the system will continue. Okay. About services, we might have 2 services. The one of the queue with one job, and the one from the queue with 2 jobs. Okay? So, if it is the one with the queue of one job, it will go here, because we will be in one state where the one with one job now has become empty, and the other remains with 2 jobs, so in the 1, 0, 1. If it happens from the one with 2 jobs, we will go to one state in which both queues have 2 jobs. Okay? This is finished, and in the last case, any of the 2 queues will finish, so we have 2 queues with 2 jobs. If any of the 2 finishes, we will arrive to one state with one with 2 jobs and another with 1 job. Okay? At which rate will occur 2 times mu. Okay? Which is the solution, which hopefully is here. Okay, there is also for join the shortest queue, but we will do it next time. One exercise for you. Let me write it down. So, for the next time, you will do this small assignment. How can I use Roman letter?
F5. Я тоже растерян.
Is it too much? Let me check.
Да, я не учился. Да.
No, maybe you can do it in a
Я даже по специальности.
Oh, I think you can do this. Okay? So the same cube but with 4 and 1. Okay, let's try to do this as an exercise. Okay, we will just do one thing and then I think we can make a break. Or would you like to do a break right now? Okay, so let's do a break right now and then we will try also to see if this can be done for the join the shortest queue. Okay? After the break we will try.
Сигареты. Сигареты закрыли. Нет, ты не пойдешь. Пойдешь есть.
Ой, нет. Это нормально. Сейчас сегодня, оказывается, нужно сдавать это. Да, по диплому надо по иностранному практику сдавать и так далее. Да, вот пойду сейчас сдавать.
I think you need at least 20 minutes.
20 minutes.
I think, yes.
Ты сделала?
Usually after something like this, you are anybody would be completely
Да, второй
destroyed,
этап.
so minimum
Да,
20
но только не ее, по-моему. Не. А есть продолжение?
Нет, конец.
Нет, это формула умения. Это мобилити. Не, у меня этого нет.
А это не этого, не Джузеппе?
Не. Джузеппе.
Ебать, у нас с тобой разные
Еще первый листочек должен быть.
У нас с тобой разные формулы.
Не, просто, короче, в этом листе, в доке, там есть формулы для вероятность мобильная, в общем, они переходят постоянно из одного в другую.
Да, это для
вот.
меня.
Это вот у тебя, а у меня без этого.
Да?
У меня
Просто мне нужно найти эту формулу. Я нашла P, N. Мне нужно найти это. Чтобы найти это, мне нужно разбивать тоже на кольца.
Ну, так это в любом случае. Там просто вероятность
разбивала на
используется.
кольца.
Ой, я в этом сначала путался, но потом я привык, в принципе. Ну, короче, не сложно. Вот у тебя есть, типа, группа. Сейчас.
А ты не вот так разбивал на кольца? Это вот это мой чуть-чуть, да? Привет! Привет!
Так радуется.
Да.
Согласен.
Короче, я тебе не могу сказать, типа, формулу знаю, нет, я тебе могу чисто на примере показать. Вот, сейчас. Вот если типа есть группа. Вот если типа есть группа, там 2, 4,
Это я
5,
знаю.
вот,
Это
смотри.
я знаю.
И как разбивать на кольца. Это
Это
сначала.
я знаю. Так не всего до конца будет.
Тогда там вот так вот, допустим. Вот так.
Я поняла, да.
Или
по-другому.
Да.
Я это не знаю.
Так, а чего ты не
Программу надо сделать.
Ну,
Ладно, Армен, у меня появилась идея.
Хорошая или...
Хорошая. Разбить на кольца и все сделать.
Я хочу уйти.
Лямку, блядь, еще понял.
Лер, мы ищем лямбду, пока.
Сорян. Она прям дикая лямка.
Лямбду.
Где у нас листочки она сделана?
I'm not sure I have one.
Никто не забыл расписаться?
No, for example, every cube once is.
Okay.
For example, 2 for 4 cubes
Понятно?
Да, все понятно. Да, ну, просто мне запутаться, мне надо зайти еще раз на работу.
Расписали, да?
Да, все сделал.
Следующая лекция будет в четверг.
Да, я знаю. А сегодня будет еще?
Сейчас, да, перерыв, продолжение.
То есть, в принципе, ничего закрывать не надо.
А?
Ничего закрывать не
Я
надо.
Вы тоже с концами ходите? С концами ходите? Еще вторая лекция.
Если нам нужно к научному руководителю по диплому подойти.
Кто у вас руководитель?
Гайдамак Юрий Васильевич.
Скажите, Юрий Васильевич, что лекция продолжается.
Но она просто в 5 ходит уже, к
So
сожалению.
they are identical.
Я даже не знаю. Я спрошу.
Just simply count how many are there.
Maybe for 5 views,
Ну, надо.
more things.
Exactly.
That
They must be
maybe 10
identical.
views, I use one, no problem.
No problem. But you might also have, you can also handle cases in which, for example, you have 3 of one type, and let's say another is of another type, so maybe you might also have cases like this.
This is 5.
Yes, but they are different, so you will need to group.
Yes.
Different group, and so the state will be slightly more complex because you have to know how many in any in the combination.
Here lambda,
Yeah.
here lambda,
You might have also different groups, but you are different. All these are identical. So if they are identical, you might do something. Okay? This case, for example, that is called lumpability.
Про Андрея, про Молчана, потому что я боюсь, что таких правил с работы, что реально работать, да, наверное, их не было.
So there is everything is called.
Ну, ты спроси у Пирогова, потому что Пирогов говорит, что ведущий курс.
Okay, and there are some conditions. So if you read the paper about lumpability, they will tell you in general which condition must be true for being able to do something like this.
Здесь вы остаетесь, да? Можно остаться здесь сейчас, да? Вы не уходите.
De rectifier des choses dedans.
Ça c'est pour ça.
Non, c'est la chose médico-pratique.
C'est beaucoup comme ça.
Oui.
Tu dois rectifier quoi?
Je vais laisser la changer seulement les choses dedans. Bon, pas changer juste les trucs disant comme abréviation, ce que je devais mettre. Depuis que je lui ai envoyé l'article là, il n'a pas encore regardé. C'est quand il le voit même. Elle a dit d'envoyer ça.
Il faut le motiver quoi. Si tu le lèves,
C'est qui l'article?
Non, pas comme si la liste n'avait pas se vite avec la
ça, est-ce que maintenant vous avez...
Ой, можно выйти?
Oui.
Comme ça? Oui, là c'est bon, quand même, ça va vous aider. Hein.
Quand j'ai dit ça depuis, je ne savais pas se vite avec ça.
Tu vas voir.
Même à titre de ça,
А может собирается что-то? У нас сегодня даже английский. Ну, банально все.
ça, je ne sais pas, avant il n'y a pas de système. Peut-être que c'est cette année, ils ont changé.
Она у нее класс, но если она может учиться,
Si tu as un article
поэтому я думаю, она класс. Но мне кажется, это просто тех, кто не появляется, не собирается учиться,
Mais tu vas faire ça, si tu es
не собирается на
Ah, le jeu que tu veux. Comment là c'est bon? Comme ça, le thé même le jeu que tu as affronté aussi, tu sais que tu as. Mais ça va compter. Voilà. C'est très bien.
Quel malheur là. Quel malheur nous avons. Maintenant, nous, on n'a pas le choix.
C'est maintenant, tu vois, tout l'été africain, tu n'avais pas de l'eau. Il fait jusqu'à la fin. C'était, je ne sais pas, il y a une autre truc. Maintenant, tout le pays africain est de là. Il n'y a pas, c'est tout le pays par le fond. C'est pas de développement.
Еще спрашивают меня, как я могу сказать, что все это.
Depuis que j'ai envoyé, on m'a dit de ne pas être là.
Tu as envoyé ça.
J'ai envoyé.
Не, я хотела хотя бы даже на тройку оставаться. И но суть в том, что даже вот если когда ты решил фамилию называть, сложно.
C'est le système, tu te dis ça,
Дело в том, что мы вроде как можем посчитать, а все равно дофига. И я просто не знаю, как я это делала. У меня вот за выходные не получается даже философию делать, чтобы за выходные успела все сделать. Да, еще у тебя будет звонить начальник, типа Мария.
Ma femme, il est bien.
Сегодня там
Je n'ai pas fait ça.
работа над проектом, и там вот задание какое-то, и все. Ну там единицу я так рассказываю, я вот там по работе, я а мы идем вообще даже на работе есть там, ну ладно, можно там свободную минутку, может не будет, на работе нет свободной минутки. Нет, я не знаю, почему она так делает. Опыт в том, что ничего, погода, опыт. Я не знаю, что не изменится. Не, я понимаю, что допуск я не верю, ну, допустим, вот полгода перед этим диплом писать уже как бы лучше. То есть наш диплом только был создать, естественно, можно еще готовиться. Но все равно, как бы, даже если полгода запаса, это будет тяжело. Зависит от того, как вообще справляешься, наверное. Просто, если тебе вот норм, если ты, мне кажется, у нас в универе, если ты вот решил не отчисляться, вот именно действительно не отчисляться, то, в принципе, ты можешь как-нибудь там, может, выучиться, сдаваешься, можно. Но все равно это такая, Мне кажется, Маша
такой
заразучка. Ну, потому что, хотела, но, по-моему, сказала, что можно потом сделать. Когда вот вы уже на поле,
Elle a fait quoi?
вот,
Elle a fait quoi?
типа, вот первый, второй, когда можно было, если это все закончить, тогда можно делать. Ну, то есть, мне кажется,
Peut-être que vous prenez le cas.
ну, не то, что
C'est pas les entrées.
сначала помочь,
ну, да.
два-три раза, еще через неделю, потом еще не факт, что ты сессию вернешь.
C'était lui.
Какую шишечку я говорила. Знаешь, что я
Ну, это да, отдельно
C'est pas les entrées. Parce que les gars aussi, c'est
У
pas.
нас тоже, мне кажется, сейчас было чисто.
L'autre, je ne sais pas, il dépasse un peu parce que fait des trucs de l'autre, il connaît des trucs qui est étranger, l'autre ne sait pas.
не просто делать,
C'est un jean, le mec.
Moi, je ne sais pas si c'est quelque chose qui
Хотя
a
бы надо свой
réussi
вкус точно определить в отношении, что ты хочешь. По нему жестко следовать.
c'est
Maman,
un
si-
qui peut gérer ce pays à part lui?
Non, non, il ne faut pas dire ça.
Non,
Si c'est certain,
non, mais c'est juste
parce
la
que
vérité.
il ne faut pas dire. Non, là, c'est pas parce que ici, la Russie, c'est vaste. Mais certains gens là, on ne connaît pas. Bon, je sais que. Je ne déclare pas. Mais il y a des gens. Peut-être qu'il ne faut pas dire que si c'est pas lui, il n'y a pas quelqu'un d'autre qui peut qualifier la Russie. Lui aussi, entre-temps, est-ce que c'est. On l'a proposé seulement, est-ce qu'on sait qu'il est parmi les compétents? Entre-temps, qui est président?
Мне кажется, вообще
Celui qui est dans la Russie, c'est qui? Gorbatchev. Gorbatchev, c'est qui? Parce que moi, j'ai vu que c'est vrai, même s'il n'y a pas quelqu'un, peut-être ils vont mettre quelqu'un et ils vont le former quand même.
Это настолько другая ментальность, то, что
Qui est ça la personne qui sera là, c'est Poutine qui va gérer. Quelle que soit la personne, c'est lui qui va gérer.
самый большой страх у нас какой? Не закрыть. Вот, с первого раза. Короче, они крутой. И кто может Блин, это ощущение, что эти прям конкретные.
Ce sera beaucoup. À part, non, exemple, vous allez dire qu'à part lui, il n'y a pas quelqu'un qui va diriger la Russie. Hein?
Il y a déjà qui sont dits comme lui.
C'est ça, mais c'est
Il y en a, donc il y a déjà qui sont dits.
Voilà.
Ils sont déjà dans le sécurité. C'est pas la vie qui a pas.
C'est ça.
Non, ça je sais pas.
Oui.
Je sais pas.
Parfois, on arrive certains gens, surtout les militants, qui vont dire que non, le président, c'est les partis là. Il n'y a pas quelqu'un qui va les remplacer. Mais moi, je vois.
Puis c'est le chien. Puis c'est le chien. Non, c'est un président dans le monde que moi je respecte. J'aime sa manière de riposte, de je sais pas quoi. J'aime sa manière de diriger. Quel que soit le problème, je respecte ça. C'est possible de faire ça à l'envers. Lui-même, il ne sait pas. J'ai l'impression qu'il n'a pas l'idée de ce qu'on doit mettre dans le guide, tu vois.
Moi, je disais que maintenant, il n'a pas que c'est que ton diplôme. Il va te dire, viens, tu vas assister au séminaire, viens, tu vas faire tout ça. Ça va te motiver. Ça ne reste que combien de jours?
Pour toi, c'est la dernière année.
C'est 12 jours.
Oui, c'est le jour de l'animation.
Gibson, ça te reste 12 jours.
Tu fais jusqu'à maintenant espagnol ou
Pardon?
tu fais espagnol?
Non.
Vous avez quoi comme là? Même magistrat,
Russe, oui.
comme ça? Il n'y a pas, ça dit que même en anglais aussi, il y en a. Non, non, c'est comme un magistrat. Non, c'est pas. Il y a un professeur comme ça, comme vous voyez, il n'y a pas.
On fait le cours d'anglais. Mais c'était 3 secondes, c'est le on a fait ça le semestre passé. Premier, deuxième, troisième.
Ah, c'est ça.
Tu vois, déjà, j'ai écouté ces questions de procédure.
Call it Ita. C'est collé. Ita, c'est collé.
Какой закон? Это теоретическая часть. Много?
Страница 30. Ну, каждый раздел по странице 3, наверное. Получается, раздел пункт.
По 30 страниц?
3. У меня 30 страниц всего. Ну, первый раздел. Первый раздел, 30 страниц всего.
А всего сколько?
Пока не сколько.
Не, ну всего страниц.
Пока их нет.
Ты их не понял.
У меня же нет диплома.
Вообще?
Нет, у меня есть первый раздел. И начало второго.
Ну, они написаны тут. Или они просто какие-то статьи, которые тебе нужно будет ставить?
Вот.
И все.
У меня первый раздел 9 страниц получается. Ну, уже диплом готов.
Я не готов. Я первый раз пришел с 27 страниц, я говорю, у всех столько мало? Он говорит, ну только у вас, типа. Сегодня ко мне все приходили, у всех нормально, как бы по 40.
Как у меня, знаешь, такая что-то листает, и такая, и все. Такая, реально, вот такой интонация. И это все.
Ну я потом перевел, у меня теоретической части не было, я потом перевел, и нормально. Странички появились.
У тебя проба большая?
Да небольшая, нельзя код ставить, понимаешь? Ну нет, потому что...
Ну, это не считается, да, я знаю.
Да, я
Ну,
ставлю
просто
чисто
она
как
большая,
проект.
просто мне сейчас получается она будет большая. У меня, во-первых, две прозы, во-вторых, нихера большие.
По ходу ты имеешь в виду?
Да, очень большие.
Ну, так это ж круто. Ставишь
Не
код,
уверена.
займешь
Просто они
странички.
мне такие, что вы такое дописывали? Это вообще я с ней никогда не работала.
А я такой, ну знаете, мы сидели с Арменом. Я ему говорила, что делать, он делал.
А ты на Яве писал?
Я?
Армен?
Третий курсник. Это в команде.
Нифига себе.
Ты на Яве писал?
У меня много ошибок было.
Писарь.
У меня как-то скачала Яву и такая, как не работает, непонятно.
Влад, кстати, разбирается.
Ну ладно.
Мне скинули там просто приложуху, типа ты меняешь значение, и там на экране высвечиваются разные треугольнички. Вот это меня забавило. Все.
Ну, она мне сначала у меня было очень все неправильно. Хорошо, что ты скинул этот вот пример. Потому что если бы я еще типа и саму курсовую оформил, я думаю, что будет полностью.
Да, видела твою курсовую просто. Вот так вот картин,
Да.
формулы картинками вылезаны.
Где ты видел мою курсовую?
Когда мы сдавали.
Курсовую? А что за курсовую?
Мы сдавали в январе.
Я не помню.
Ты перегрелся?
Я просто
А ты в
потерял.
куртке, кстати, нет?
Да, на вещице.
Мы спорили, зимняя куда?
Не зимняя. Но мог бы я в зимний, конечно, ходить. Я обычно снимаю зимнюю куртку, когда это
Совсем.
совсем.
Кирпичок, да?
Сейчас, в принципе, уже без куртки можно.
Томск готов сделать презентацию?
Нет. Я сделаю, ну, прям, наверное, 20-го.
В самолете, да?
В самолете презентацию.
А это, кстати, хотел узнать, Марта Вилка, она женщина или это какая-то?
Или это что?
Или это девушка какая-то, ну, типа там...
Женщина. Женщина.
К ней Марка просто.
Ну, это вот я что-то тоже как Марта общался.
Я к ней просто здравствуйте. Можно?
Она как вот ты позвонила, кто-то мне написал, что она позвонит, она позвонила, срочно, и все, больше не звонила.
Немного нарушаем законы с Мишей. Передаем.
Опасные люди.
Передаем информацию.
Секретную информацию.
Давай, еще подзадорим максимально попытаться. Давай, я люблю это.
Марку под суд подводим.
Да.
Кстати, эта конференция, оказывается, ну вы же пробацию добавляли тоже?
Да.
Потом сколько?
Да.
Она, оказывается, ну я узнал, что она к программному обеспечению. А что мы там делаем? Ну, конференция, типа, разработка что-то программного обеспечения.
Я не знаю. Экономических моделей. Да.
Да. И что мы там делаем?
Ну, типа, вот ты свое делаешь, ты делаешь это. Ты делаешь то, что ты делаешь, и мы делаем то, что мы делаем. Да, и вот это и есть, да, это как медалка. Нет, ну потому что девушки едут, они из бизнес-процесса не едут, например.
Ну, типа программа какая-то.
Верно, да.
Okay, so are we ready to start? Okay, it was a long break, but I think it was necessary. Do you think somebody else will came back? Oops. So can I start? Should we wait for some people somewhere else looking on that stuff?
I can change my position.
No, it's no problem for me. I think you are not bothering them too much, otherwise they would have complained. So. So, one final time this type of game, just to show that, okay, this concept belongs to something more large that is called lumpability, and if you look in the literature, you can look for Markov chain lumpability, and there are a lot of theorems and definitions that allow you to apply this type of reasoning to reduce the state space of models. Just to show you how powerful it is, we can apply the same type of reasoning also for the join the shortest queue case. Okay? So, again, if we have this system in which we have the 2Q, and now we both Q have capacity 2, and when a job arrives, it will join the shortest one, can be still something that can be expressed in this framework. Okay, so again, we start with an initial state in which we have 2 empty Q, 0 with 1 and 0 with 2. Okay, if a job arrived, we'll go to any of the Q independently. So at rate lambda, the full arrival rate, they will move to any of the TQ, but in any case, they will go to one state in which we have 1 empty and 1 with 1 job. So this is exactly the same. When we have 1 with 1 job and the other empty, we might have the service of the job being served. The difference with before is that now, if a job arrives, for sure it will join the empty queue. So, while before we had that if a job arrives with half lambda, it will join the first queue, with the other half lambda will join the second one, the one with one job. Here, it can only join the queue that is empty, okay? Because this works in this way. So, we join the shortest queue. If another job arrives, for sure it will move the system in a state in which we will have 2 queue with 1 job there. Okay? Here we might only have 1 service of any of the 2, and if we have 1 service, we will arrive to the system in which we have 1 with 1 job and the other with empty. So at rate 2 mu, because now there are 2 jobs in service, we will move up. In this case, if another job arrives, it will randomly choose either this one or the other, because they are either the QA or QB at equal probability. So at rate lambda, we will move to one state in which we have 0 empty, 1 with 1 and 1 with 2. Okay? From this state, again, we might have one arrival that will move the system for sure to the state with 2 empty full Q. So it will go to state 0, 0, 2. Okay? And if we have one service, the service can be from the queue that has 2 jobs, and in this case it will go to state 0 to 0. But we might also have the case in which the service will be from the queue that has 1 job. And in this case, it will put the system to an unbalanced case where we will have 1 empty queue and 1 with 2 jobs. Okay? Which is this strange state up there. From the last state, we can only have services because now any arrival will be lost since both servers are full. And since we have 2 in parallel, the rate will be 2 times speed. Okay? From this state over here, we might have 1 arrival. If we have 1 arrival, it will be routed for sure to the empty queue. So we will move to this state where we have 1 empty and 1 full. Or the only service that we have can be from the station that has 2 jobs. And in that case, if it is served, that will reduce from 2 to 1, moving to one state in which we have 1 empty and 1 with 2 jobs. So at the rate mu, we will go back there. Okay? And here you can see the 2 lamp Markov chain of the 2 processes. Okay? So, this should have been the easy part. What you should have known from your previous knowledge. Well, maybe this way of looking at things could have been new, but after having understood all this type of watching the system works, you should have been able to do this. Okay? Okay. So, the main idea is try to exploit what we have done here to create this state space to provide some approximation to the behavior of the system so that we can further reduce the complexity of the model. This already reduces a lot of the complexity. From the initial case where we said that for NQ with capacity K, we need K plus 1 at the power of n state, we have moved to this that still have an exponential growth, but much less. In this case, we need something like n plus K minus 1 over, I don't remember if it is K minus 1 or n minus 1. I don't remember which of the two. But it is the same as the number of states you will have in a closed system Q with NQ, with KQ and N customer. Okay? Another way of looking at this system is imagine that you have 3 different queues in a whose population is equal to the number of stations that you have. So each of this queue will represent the system with a given in a given state, and jobs will move inside that at a given point. This is a way of seeing it. So for this parallelism, you can say that the number of states that you will need to encode this type of system will be equal to the number of states you have that type of system, which is something like that. I'm not sure whether it's k or n. I'm not even sure if it is +1 or -1, but you might check. Here was it working? It would have been 3 over 2, which is 6. So probably it is +1.
I have your work where you
Okay, yes, perfect.
where you wrote
Okay,
to lambda,
okay.
and now you write one lambda. It's
Okay.
mistake or
No, because in that work over there, the arrival rate was 2 lambda.
okay.
So it was basically the same model, but for some reason we put 2 lambda in the beginning. So everything is multiplied by 2. There was, I don't remember, and this is the formula that I was referring to now.
Okay.
So it's here it was 2 lambda the arrival rate.
Okay.
I don't remember where it is written, but somewhere there's written 2 lambda.
Thanks.
Okay. So the main thing that we have to keep from all these game we've played is the change of forms. We first of all consider a system of identical entities, and identical entities can be in a certain sense quite complex, like in the joint of shortest queue, because the jobs would have moved to one or to the other depending on how many jobs were there. But the decision in any case was done each queue in the same way. So it doesn't matter which queue have 5 customers and which 2. The only thing that matters is that we have one that has less job than the other, so the new customer will go there. Okay? Everything is identical when the system has the same state, have the same number of things in the same group. Okay? So each entity is characterized by the set of states among which it evolves. So in this case, each entity was characterized by the number of jobs in the queue, but in other example, it can be considered in a different way. Okay? And the state of the continuous Democrat chain was counting the number of entities in each state. Okay? In this case, we can call this a counting process, because the things in which we were interested is the count, the number of entities in a given state. Counting process, we do not model the state of the process, but the count of entities in that particular state. And this is the main change of vision that we need to do to move to min-field model. Okay? Okay. So, let us look now at the system in a different way. So, this is a system where we have 2 entities. Okay? But what happens if I focus on a single entity? Okay? I have 2 queues, but if I focus on one queue, in the random routing, the behavior of the queue is something that is independent from the system. So, let me focus on one queue. I'm focusing on this. This can be empty, can have one job, or can have two jobs. In the random policy, it doesn't matter what the other is doing. In case, a new job will arrive at speed lambda half, because it will be assigned for sure to the station. In any case, if we have one job, we will move to the state in which we have two jobs, regardless of what the other station is doing. Okay? If we have one job in the queue, we will have one service, and if there is the service, our state will become empty. If we have two, we might have one service, and if it occurs, our state will become empty. Okay? This is the evolution of one agent. So, how can we, in some sense, use this evolution of one agent to create the evolution of the system? Well, if the system isn't lambda, as in the figure over here, you see the pattern here that describes the behavior of one agent is repeated horizontally and vertically, because they are independent. So in every state, the first component evolves like this agent, the second component evolves like that agent, all in the same way. Okay? But can from that also consider the lambda model? So, from what we have here, lambda half, can we see the things that we have there? Well, in a certain sense, yes. Because this lumped state over here counts how many agents are in a particular state. So, when I am in this state 200, I have two agents, each of the one is moving to state 1 at rate lambda half. So, since I have two that moves at lambda half to state 1, to state 1, I have that the next move of the system will be from one agent in state 0 to one agent in state 1, the first of the two that will perform that move. At speed 2 times the one that one single agent will do. Okay? This is state 0. Here is telling me that I have two agents in state 0. Each of the agents in state 0 can do.
I missed this state transition diagram. The first component describes which situation.
Okay, sorry. This was the lambda state in which we have moved from one description in which we have for each queue the number of jobs that we have, to the other in which we count how many queues are in a given state. So, here, in the first aggregation, we have that we have 2 queues with 0 customer, 1 queue with 0, 1 queue with 1, 0 with 2, etc., etc. Okay? And so, in the end of the last hour, we played to create this game for the join the shortest queue, which reduces a bit the state space. Okay? So, this reduction can also be done here. And in this case, we start from 2, can do a move at rate lambda. So from here, we go to the state at 2 lambda half. Okay? Here, from state 1, we move to state 2. When we go here, we have 2 in state 1. So from this, we can go ether at rate 2 times lambda half, or they can move backward at right 2 mu, which is what we see here, where we have the 2 mu that goes up and the lambda that goes down. Can you see it? This is the hardest part to see. But can you look? Here I have the counted process. Counts that there are 2 in state 0. So the rate that goes here, since from 0 we have just one transition out, we have one transition out at twice the rate, because we have 2 at rate lambda half. In the other state in which I have 2, here I will have 2 agents in state 1. In state 1, one agent can go to state 2 or state 0. I have 2 agents in state 1, so they will go to state 2. One will move at state 2 at 2 times the rate, and this will be the state 0, 1, 1. Or it might go back at 2 times the rate, so 2, it returns upstairs. And even in this case, in state 2, we have just mu. So if we have 2 in state 2, they go up in that state. Okay? What happens when I have 1 and 1? So I have one agent in state 0, which can move at lambda half to state 1. So from this state here, when this moves to lambda 1, I will arrive 2 at the rate lambda 2 that I see here. I'm not sure if you can see this. Maybe this is better. Okay? But since I have 1 in state 1, I can also have at lambda 2 that one that goes to 2, which will be this transition here, and at mu, that one that goes to 0, which will be the transition back there. So there is a way in which, if we have the behavior of one agent, we can build the lumped state of the system. Because in each state, we will consider this rule that we see here, how many I have in that state. So I have 2, I will use 2 times the rule from state 0, and 0 the other. Here I will use 1 time the rule from state 0 and 1 time the rule from state 1. Okay, and here I will use 2 times the rule from state 1. Here I will use 2 times the rule from state 2. Here I will use 1 time the rule from state 1 and 1 time the rule from state 2. And by combining everything, I can came from this state to that other one. Okay? So, even if probably is not that clear the complete procedure, which is not hard, but probably we need to do it manually a few times to see the point. But understanding how to do that is not the key. What is interesting is that there is a connection from the description of what one agent does to how we can build that combined state space. Okay? Okay. But this is because this agent is particularly stupid, since it always moves in the same way. If we return to this one, which probably was even easier to see, even if it has a lot of state, everybody behaves always in the same way. The question is, can we have an agent-centric behavior also in more complex cases like this one? So here we were saying, okay, I have 2 agents and I focus on 1. Since when I know how an agent moves, I can use it to create the combined evolutionary system. Can I do something similar also in the case of the join the shortest queue? The answer is yes, but things are slightly more complex. Because in the join the shortest queue case, I cannot move from state 0 to state 1 regardless of where the other agent is. Okay? Because one job will arrive to my station only if the other is, let's say, full or have more jobs than the one that I have. Okay? One job will arrive to me only if the other are in a worse condition. If there is one queue in a better condition than mine, I will not see that job. Okay? So, if I want to move from a description of a complex system focusing on one single agent. In more complex cases, like the one join the shortest queue, I have to do some slight extension. So, for example, I can encode that type of motion if each of the station, when deciding what to do, can look at the other. So, let me say that I am station A. Okay? Let me try if I can focus this. I focus on this station. I am empty, so I am in state 0. Okay? I am in state 0. If one job arrives at rate lambda, it will join me if the other has some job. Otherwise, if the other is empty, it will go to me, half of the probability, to the other, half of the probability. Okay? If I have one job in the queue, I'm in this state, the other job will join my queue only if the other has 2. So I am the one that has one job in the queue, the other station has 2, so the next one will join me for sure. Or if the other has also one job, half of the time the new customer will join my station. The other half will join the other. And if the other is empty, the new job will never join me. Okay? So, the main difference from this case, where everything is independent, so there is no connection between the two, this case is that now, to implement the join the shortest queue, I can still do it with an agent-based vision. But now, the rate that tells how the system will move to a different state will depend on the state of the other queue. So, if the other queue is empty, it will, and I am empty, it might join me at half of the time. But if the other queue has one job in the system, it will for sure join. Okay? There are no other possibilities because I am empty. So for sure I am empty, and the new one will join me for sure if some other has more jobs than me, or will join me half of the time. But if I have one job, there are 3 possibilities. It will join me for sure if the other is 2. It will join me half of the time if the other is 1, or will not join me at all if the other is empty. Okay? So, what we have done now is just changing our vision to the system. We are going to describe the join the shortest queue policy not as a global measure, where, as before, we were trying to understand, and each time we pose our question, who is going to join the shortest or the other and decide over there. Here, we just focus on one queue, and we can say, put to this queue a behavior in join the shortest queue, like, because what we are doing, we are conditioning our evolution, our rate, on the other state of the system. In this conditioned way, we can express a complex system behavior with a local set of rules. And this is the key to be able to do mean-field modeling. Okay? But this is not something mathematical. It's something from the modeling point of view. The system that I am considering must be characterized so to properly model it in this way, so that I can model the global behavior of the system by making some of the rate functional on the state of the other queue in the system. Okay, have I been able to explain? This is the key concept of all, because this is not connected to form. It's just the language that I use to describe my system. And this is what makes mean field useful, because it can be used only if I have the possibility, yes, to express a system as a set of states and jump between states. But I must have some functional relation, so that I express the logic of the system with some function that change the way in which I move from one state to the other, depending on the states of the others. If this is possible, mean field will be useful. If this is not possible, mean field will not be the right tool that can be applied. But lucky for us, whenever we are considering the type of system that I have introduced in the beginning, these occur very frequently. Okay? Okay? And again, we can, for starting from this definition, have the way of composing them. Again, if I have 2 in state 0, then if the 2 are in state 0, the other is empty, so we will have 2 at lambda alpha. The sum of 2 of lambda alpha will be this total lambda. If I have 2 in state 1, it means that the other is state 1, so I will be considering 2 in state 1, lambda 2 times, and it will be 2 lambda, and for sure it will move at the other direction, which is that over there. But if I am in a state like the 1, 1, 0, for the Q, which is in state 0, the arrival rate will have rate lambda, because the other has more than 0. And it will be the lambda that will make this 0 go to 1 at this rate over there. For the one that is in state 1, okay, for the one that is in state 1, the other has 0, so the arrival rate will be 0. There will be no arrival rate for the one in state 1 due to the rule over here, because the other is 0. And there will only be the service at rate mu that go there. Okay? And so, again, we can, in each state, combine the rate to the other direction by using the rules, considering how many I have in that state and what the rule tells me to do. Okay? Which now is functional, that depends on the other. Okay? To put into another way, what we do when we are expressing mean field modeling, we have a Markov chain whose transition rate depends on the number of agents in other state. Okay? So, for every system in which we have many identical objects, the many identical object will behave independently, but can also make some global decision based on the entire state of the model. If this decision can be done just depending on the count on the number of objects in one state, we can apply mean field modeling in a good way. Okay? So, this can be done whenever I can express a system as a set of identical objects. Each one evolves according to a Markov chain, so we have rate, speed at which it jumps from one state to the other, but sum of the state rate depends on how many agents I have in each possible state. And this is the key of mean field. We have done all this trick today, first to be able to understand the importance of the counting process, so that we can express a system not as the state of each component, but as the number of objects in a given state. And we have seen how this can also be used to encode some policy. Next, we have seen that, okay, if we have that definition, we can express the evolution of each object as function of the order, of the count of the order. So, whenever we can define one object of a system with some behavior that depends on the count of the other objects in a given state, we can apply mean field analysis. So mean field analysis is not something general. It's something that is useful only for systems composed by large number of identical objects which all behaves in the same way, and each one has its local behavior, like in the random case where the local behavior is such that every agent completely ignores the other, because since the new customer cannot look at the agents to decide where to go, it will simply toss a coin, join any, and this is expressed by this fact that there is no interaction, up to more complex behavior where the decision of who join next will depend on the count of objects, of elements in another state. Okay? Just to give you some idea, this is a very general approach. So, for example, if we want to apply the mean field solution, we might have a system where we have n queues, and simply each of the q will have lambda divided n of the possible arrival rate. If I have a system with 10 q, I will simply have 10 of these, and if each of the q has a capacity of k, then each one will move forward up to the point in which it has reached the capacity. Because it is a random allocation, so as before, each job will randomly choose without looking at anything else. Okay? And if I want to model the job the shortest queue with MM1K station, I can do this where, again, each agent has kth state. Okay? In the state 0, it will jump to state 1 at a rate that depends on how many empty stations in the system are. If I am the only one empty, N0 will be equal to 1, because there will be only one queue empty. All the jobs will go there. Okay? If we are in the case in which we have five queues, okay, and of these 5 queues, 3 have some job, and 2 are empty. The new job will go half of the time to this, half to this other. So this will be one state in which we will say that we will have 2 empty, and then the other will be different. So for example, we will have 0 with 1, 2 with 2, and 1 with 3 in this particular representation. So since I have 2 with 0 jobs, for the queue that are in the empty state will go there at rate lambda divided by 2. Because we have 2. If we have n0, each of the n of this empty queue, and there are n0 empty queue, will receive job at rate lambda divided n0. Is it okay for this? Okay. Let us move to state 1. State 1, we have that our queue has one job. What can be? It can be that if some queue is empty, so there is at least one queue with n0, in 0 is at least 1, we have at least one empty queue. The next job will go there, so it cannot go to me. But if there are no empty queue, in that case I will have to count how many have one job. If n1 is the number of stations that have one job, they will for sure reach that queue. Okay? Sorry, the rate will be divided between the n1 that have one job in the queue. So if we are in a case like this, where now we have, for example, no empty queue, we have 3 with 1 job, 1 with 2 and 1 with 3, then each of these will receive job at rate lambda divided by 3. Okay, because lambda will randomly choose any of the 3. So I will move at that. The last one will receive job only if no q has less than k, no, the q with k minus, no job with less than k minus 1 customer will be there. So I can go to k only if all the q have k minus 1 job. If there is at least 1 q with less than k minus 1, the new customer will go there. Okay? So this last transition from state k minus 1 to state k will occur only if there are no job with less than k minus 1 job, and there are n k minus 1 at rate lambda divided n k minus 1, which must be greater than 1 because we have at least that one. Okay? So, this is the way in which things works. So, these are functions, okay? We can put, as we've said, everything into a functional rate like this, okay? If we have this function, we can create a sort of infinitesimal generator where instead of putting a fixed rate, we put a rate that includes this dependency on the number of jobs. Okay? So it is an infinitesimal generator where each q has, each rate is a function of the total state. So this infinitesimal generator is not something fixed as in conventional Markov chain, but it has something that depends on the number of entities with a given state. Okay? So I might have 5 q that are empty, 2 q that have 1 job, and 6 q that have 2 jobs. This infinitesimal generator will have some special value that depends on this particular structure, on this particular number of jobs that I have in the system. Okay? I can put it here. I will call this matrix K, just to give it simple. Now, the mean field theory says that if we are not interested in the probability of a given state, what we were studying here, both in this case and in this case over here, was the probability of being in a single state. So in a state where I have 2 empty, 0 with 1 and 0 with 2, or the probability of being in a state where I have 1 empty, 1 with 1 and 0 with 2. Okay? Here I was having the probabilities. If I'm not in this situation, okay, I'm not in that case, but I am interested in the average number of jobs in a given state. So for example, I'm interested to know that on the average I will have 1.5 stations that are empty and 0.5 stations that have 1 job in the system, and 0 stations that are empty, that have 2 jobs in the system. Okay? If that is what I'm interested in, not a probability but an average, the mean field theorem tells that I can express the evolution of the number of objects in a given state with a differential equation that is very similar to the standard Chapman-Kolmogorov equation for transient analysis of Markov chain, but that works not on the probability, on the average number of entity in a given state. Okay? No, perfect. And the matrix now depends on the average. Okay? Now please, if you have some comment, I will be happy to discuss them.
Есть ли вопросы? Понятно?
Okay? So this is the magic part. If this happens, we can do this and approximate this transient evolution. Now, within a while, I have arrived very late this morning because I wanted to put you the proof of this derivation. But unfortunately, although it's feasible, I tried to simplify as much as possible and it still was too elaborate for doing in a course like this. So I have not put it, but I just put some outline on how you can write it. You can write it by first writing the full balance equation for the system, exploiting the definition of this matrix K, which is basically write in a formal way that step that I was doing before of moving from this to that one. Okay, it's not very difficult because in every state you have to consider that you have n in state 2. So for the n in state 2 I will move according to the rule 0, n1 in state 1, for which I will move in according to rule 1, etc. etc. So first I can write a proper system of equation for the full complete set of possibilities. So for all the cases here, I can write a set of equations and write the standard Chapman-Kolmogorov equation for this system over here, where the transition rates are computed starting from matrix K using the functional definition and this type of aggregation that I briefly showed you in an informal way here. Okay, I can formalize it. It is just a question of summing over all the possible states for each state, multiply the number of elements that I have, and consider matrix K in that direction for those states. So this would be the first step that I have to do. Then, after I have write that full equation for all the states and the Chapman-Kolmogorov equation, I can take the average of the solution. Chapman-Kolmogorov equation is about probabilities, so with a probability I can compute an average of something, E of something. I can compute E of state 1, for which I will sum up the number of jobs n1 times the probability of having n1 here plus all the other possibility. That's what I will do for an average. I can take the average in the Chapman-Kolmogorov equation. Then, by doing one approximation, that is what the min-fits allows, so to instead of making the average of the function of the random variable, I do the function of the average of the random variable, which is the key difference of the mean field. We arrive to the equation over there. Okay, so these are all the steps that should be done for moving from this definition of the system with this equation to arrive to that differential equation. It's not impossible, but it is very, very long. So I have tried to see if I could reduce it to something manageable, but I failed, and in that case I just wrote you an outline. Because I think the most important part is changing the vision of looking at the system. Okay? Once we have changed the vision of looking at the system, then this will allow us to find interesting results with simple equation. So what happens if we write the matrix in this form, and we use this type of definition for considering the shortest queue. Well, we can find some idea. So, for example, we can compute the queue length probability in steady state with a different number of jobs in the system. Okay? With a different number of stations. If I want to compute this set, analyze a system, for example, in which I have n equal to 100 identical queue. Okay, I have 100 queue. If I apply any of the techniques that we've seen before, even the lumping one, even if k is very small, I can still have a huge number of states which is not manageable. Because if I have a system with n entities of k state, each it evolves in something like n plus k minus 1 and until k minus 1, or n minus 1, I don't remember, but it is still exponential because these have two factorials, one of the numerator, one of the denominator, so it is less, it grows slower than k plus 1 of the power of n, but it still grows very rapidly. Here, instead, we have a differential equation that has a vector of component of the counts of the number of jobs in a given state. So it's a differential equation where we have n0, n1, n2. It's something that is linear in k. And the number of q that I have will not change the model, but will simply change the initial condition of the system. Because if the system starts with everything is empty, we will know that this vector times 0 will have all the n jobs, all the n cube in the empty state and none in the other state. Okay? So, the incredible potentiality of this equation is that with this vision, when we move to a Q-centric vision of the problem, then we might arrive to a differential equation that has as main known as the state of the system. And the number of objects that we have no longer plays a role. So the model will work as well with n equal to 100, with n equal to 1000, with n equal to 1 million. Okay? And to make things even more incredible for mean field, this theorem by Kurz that describes the mean field solution also states that the method becomes more and more accurate as n increases. So we move from the classical point of view that when a system is larger is more difficult to a vision where when the system is larger the solution is more accurate, which is totally the opposite. Are there in reality systems that are so large? Once upon a time it wasn't the case, but as we've seen in the beginning, all these new things from big data stuff have hundreds of things that work together in the same way to cooperate. Whenever you want to have traffic generated by a mobile phone, you have numbers that are huge. And so, whenever you have identical things that work in the same way, and they are in incredible large number, and you can compute the performances just starting from the mean, if you can express everything with just one single agent, you can do whatever you want. Okay? And the larger is the number of agents, the better you do. So here, in the paper from which I took this figure, this was also seen the analytical limiting solution, and it was showing that indeed as n increases is tending to the analytical solution. There was also the proof that if we consider the distribution of the numbers of Q in a given state, for example in the empty state, we see that the distribution tends to become something that seems to be a Gaussian distribution, centered in a mean value, and as n becomes bigger and bigger, these distributions tend to be picked, and then everything tends to become deterministic, which is what the mean fields want, but also was showing that if the system is good and stable, even if n is very small, like for example 2 or 3, the solution, provided that the mean field, that is this constant line, would be very close to the solution proposed by the by a discrete event simulation of the same system. So here we have tried both mean field and simulation with 2 and 3 capacity of the Q, increasing the number of Qs. So if the arrival rate and the service rate are such that the system is stable, even if n is very small, so as I told you that this application became more and more accurate as n increased, we have good result. But if the system is close to the instability, so either because it is just slightly with a utilization of 99%, or if it has some overflow, so it is, yes, it is overflowing, but its utilization would be 101%, so just a little bit outside, then the mean field will require a lot of entities so that the approximation provided will correspond to the exact result. Okay, and here you see that you need something in the order of 1,000 when you have this type of utilization, so that the mean field solution is proper to that. And there are also some cases in which the mean field solution will always provide the wrong answer, but I haven't entered too much in detail. So, I would like to conclude with some conclusion. So, mean field modeling means changing the way in which we think a system. The idea is to imagine it composed by a number of identical entities that can be in different states. We are only interested in the number of entities in a given state. It doesn't matter that there are 3 in empty and 3 full. Doesn't matter. It's just important to know that on the average 3 will be empty and 5 will be full. Okay. The behavior of one agent can only depend on the count, on nothing else, and even the performance indexes we are interested in can be computed only from the number of agents. Okay? If that works, then we can do a lot of things. And next time we will see some examples, and then we will move to Markovian agent, where we exploit this type of computation to make spatial model of things that moves in space. One final point, there is one proposed exercise, which is completely not easy, but I think we can start do it together in the last 3 minutes or 5 if we can spend a few extra minutes here. But this is just to help you thinking in the right way. So, imagine that we have one system that is composed by n users. Okay, so I have my population of n users. Okay, each user has his own mobile phone. Okay, and it might connect to the internet using either Wi-Fi or LTE. Okay, so each user has some think time exponentially distributed with an average of z second. Then, after it has spent the time, it will start sending something with his mobile phone. Okay? Let us imagine that the Wi-Fi and the LTE are at different speed. Wi-Fi goes at speed mu Wi-Fi, LTE goes at speed mu LTE. And if we have n users of that technology, the technology will be equally shared between the users. So if I have the LTE is 30 megabytes per second, I have 3 users, each user will get 10 megabytes per second. Okay? The idea is that everybody knows exactly how many users are using a given technology and chooses to use the one that will give them the shortest, the best performance. Okay? So this is a classical example of what might be very well captured using mean field model. Okay? I will just give you a hint, and then the exercise will be try for you to complete it, and maybe use your mathematical knowledge also to try to write this equation and solve it, but we will start with the solution of this next time. So we have that the user might initially thinking, then after it think, it will join at 1 over c times something, the transmission using Wi-Fi, and then otherwise at 1 over z times some other function will join the LTE. Okay? And this function will define the will reflect the behavior of the user by knowing how many are using Wi-Fi and how many are using LTE, choose to go to the technology which provides the best service. Something similar to what was here in choosing whether it is empty or not. Okay? And of course, when it is in Wi-Fi, it will return to the thin time at a speed mu, which, however, will depend on something that includes the fact that the rate is shared by the user of the same technology. Okay? And the same will be here. So here we will have the mu of the Wi-Fi plus some function, and here we will have the mu of LTE plus some function. Okay? So the exercise is try to think at the system in this way and try to provide some function to put here to encode in an agent level based how I will choose the best technology, just knowing the fact that the unknown of the system will be the number of users that are thinking, the number of users that are using the Wi-Fi, and the number of users that are using the LTE. Okay, so this will be the vector n, that will be the unknown of the system. So how many will be using a given technology? And if we will do a differential equation on this vector n, considering one matrix K, that is an infinitesimal generator of a Markov chain like this, which however has functional rates to encode the fact that the user chooses one technology or another, will evolve in a different way. It's not easy, but the question is not arrive to the solution, but try to think in this way. Okay? Let's try to do something. It's difficult, but it's just to see if you can find one match, one point after the other. How can we let them for the slide? Because that might help. Okay, she will solve the problem and find a way to let you have in the slide, because I think it will be helpful to look at them for trying to do this exercise. Okay, but it's just this exercise is just to see if you can put together and see all the line that has guided throughout today. What made us started looking at a join the short SQ service, starting to see how we model the system, each agent evolves, how we can switch to use counts, counting how many agents are in a given state, and how we can express global decision based on the count, so to arrive to one type of differential equation that uses the count inside. And what that was, the join the short SQ, can be something more interesting and in line to some research topic. For example, deciding one user in a complex heterogeneous network scenario, when to use one technology and when to use another. Okay? Question? It's difficult, but it's just to let you think in the right way. Okay? The important is that you think and try to see if you can find the point that will lead you from this system of users that want to share the technology to the possibility of expressing the behavior of the user as some local rate, I think Z, I want to be served at rate me or at rate mu3 or mu3, but depends on how many other are using the same technology. Okay. For the most skilled of you, can also try to do this with simulation, so that the user waits Z, decides to join what technology, and then repeat it. So to compare if the two things provide similar results. Okay? Next time we will start from this and we'll go on to
Professor Berg, is it possible to put your presentation on the website of our institute? Презентация будет размещена на сайте нашего института. Сейчас я напишу. На сайте института сейчас я пишу адрес.
So the PDF is already here.
Applied Mathematics and Communication Technology. Там размещу я презентацию. Можно будет там скачать. Следующая лекция в четверг, 2 часа.
Вообще большое.
До свидания. Спасибо. А ты количество ресурсов брал автоматически сам выбираешь?
Развиваешь.
Да. А мощность?
Мощность.
Маленькая синус.
Разбивается. Включил.
А как? Ты сам задаешь изначально?
Ну ты забиваешь вот количество этих блоков ресурсов, а он уже типа алгоритм сам разбивает на все возможные стойки.
Как бы маленькая индекс?
Ну вот, типа выдается 10 блоков.
Это мощность, грубо говоря, для
Либо маленькая скорость на каждый блок.
с индексом. Да, скорость передач на каждом блоке. На каждом
А,
блоке.
нет, она не разделяется, она сразу забивается в это. Сразу в программу забивается в программу, ты ее нигде не сдаешь.
В каждом подсчете?
Ну, ИТ, да, это каждый подсчет.
Но ты ее забиваешь автоматически для каждого конца.
Да. И всего 15, типа забито, вот например, правильно 15 забито.
У меня всего 2 подсчета.
А, ну тебе надо просто назначить.
Да, то есть сама. Я так и думаю. Одну программу, когда мы специализируемся интерактивными, вторую программу, когда мы специализируемся. А потом на них ADR и все.
Ну, я хотел бы делать для мобильных, как ты делаешь. Хорошо.
So, if you can divide the class Yes, you will have time for change. That's the resistance are just walking around. You will see we have a lot of systems of linear differential equations that are that scales linearly with the classes, which is nothing Yes. These are identical. You have to use the division so that you describe the evolution of one form depending on the state of the other. If you can describe the evolution of one node depending on the count of how many of the other are in a given state, mean field will give you good results. Otherwise, it's not right. Okay. You might use that because the amount of this node will have the right range depending on the state of the other. You will have, let's say, 7 classes, but yes, 3 classes, and each of these will behave the arrival rate of this node that was lambda and cube, and what might be the transition over here, will depend not just on the count of itself, but on the count of the previous and the last one.
Well, student who's already writes out, he is analyzing the system. You don't remember the topic of multiclass. When we have a model for these objective CQX, when was you analyzed it in this model with Dario Ostapov during your master courses. Do you remember? You had a cell with 15 CQIs, and like this, tried to model the moving of users through the cell by this Curie network. It's rather large when we have even 100 users, 15 nodes. It's not so exciting.
You might see it because
but it's only to count the average number of users within the node. You don't need to
probably you can have it as it is, but we have to discuss a little bit more about the system. But it could be one case where this type of thinking might provide a good solution. Discuss some problem. I think one reason for choosing this topic is that we have constant research competition. If you see anything, it would be nice to start trying.
But I didn't understand the idea.
I understood the presentation.
The idea, because it's incredibly simple when you change the way of thinking, and it works